Thank you very much for the invitation and the opportunity to give a talk here. Well, today I won't only talk about entropic repulsion of Gaussian free field by an interval. I'll talk about many things. I had to pick something, so here it is. So it's based on our current work with the video. So, well, what I will present today is already the pieces which are done, but, well, I will try to give you a good motivation why we at all were looking at this problem and like what are the next steps towards our final goal. Okay, so coming back to spin-oil models that we had an amazing introduction to. So the only thing I would like to mention is like that one can also consider the spin-oil model with the conductances, which are basically the functions. Well, for me, they're on directed edges, where each undirected edge has a positive and a negative direction, and they are related by Cxy equal to Cyx. And why do I want these conductances? It's exactly because of this last 5 minutes of Christoph's lecture, namely to use, well, okay, we will see where I want to use it. But okay, here I just more or less repeat the slide of Christoph. So namely, well, spin-oil models at inverse temperature beta. Inverse temperature beta means that all Cxy are just for edges on our Z2 are equal to beta. And well, for these models, when n is equal to 1, we have easing. And as it was discussed, there is this order-disorder phase transition. Then for XY model, which corresponds to n equal to 2, we have a topological phase transition with vortices. And then, well, thanks to Christoph, I actually have these nice pictures. And then the n equal to greater or equal than 3 is this conjecture by Polyakov that there is no phase transition, and to some extent this was actually our motivation, and I will try to explain how I can see it. So here are the main characters of my talk. So I have directly Gaussian free field on the box lambda n, which for me is minus n half in Z2. And okay, so I have my own preferences. I use the random walk normalization, and I sum over x and y, which are the vertices. So that's why it's basically 1 over 2d 1/4. So that's a different normalization. And then we would also need n vectorial Dirichlet Gaussian free fields, which are basically just the n independent coordinate processes which are GFF on their own. Then we also have a massive one. The only difference that now, except for this term here, that would correspond basically to the discrete Laplacian, we also add some mass term over there. Well, so basically it's just a Gaussian vector with a massive Green's function as a covariance structure. And then we, again, would need the vectorial massive Gaussian free field, where we just take n independent copies of this massive GFF. And these nice simulations are available. Okay, so now I come back to this, why at all I mentioned spin systems at the very beginning. So there is this nice observation that if you look at the spins created by the GFF, and by that I mean I just look at the renormalized field, renormalized at each point, and then I condition actually on the values of the norm, then what we recover is nothing else as the spin-oil model with conductances phi x, phi y, the norm of phi x, phi y, and okay, I have this 4, which is the 2D difference. And the same holds also for the massive one, because like once we have this conditioning, like the mass sort of becomes just a constant in the Hamiltonian. Okay, And, well, here I can already reference to the paper that was presented in last 2 minutes, where this relation was exploited. And then for n equal to 1, for instance, in the paper by Titus Lupo and Vanderlindana, I think it's called something like Norton-Ising model, they exploit also this relation, and also this relation, but for higher dimensions, d equal to, I think d greater or equal than 4, it's used to get some results on the percolation, on Bernoulli percolation. This is the second paper in the n equals 1 case, and okay. We also, with my advisor, Human Arrow, we studied n to infinity case. Okay, so what's the motivation here? We want to understand the low temperature behavior of spin-ON models. And we now know that there is like some sort of relation so that one can instead look at these spins generated by the Gaussian free field. Okay, so the exact relation is that we condition on the norm to be equal to something, but what if we relax it a bit and actually start looking at the condition that the norm is at least greater than some r? So this is our starting point. But before we go there, there was actually, there are some related works which are important to mention, where the case was studied where we don't look at the norm, we don't condition on the norm to be greater or equal than r, basically we condition just on the field phi x to be greater or equal than r, and like the case which is covered in the literature is greater or equal than 0, but basically it doesn't matter whether we are looking at this thing or not. So basically what's happening here is we are looking at the event where we assume that phi x is greater or equal than 0 for all x in some Gn, which is like a nice smooth boundary subset of lambda n such that it's sort of away. This is so that we can work with the Green's function in a nice way. And then basically, so what's happening in some sense? So we have this hard wall, and then we have our GFF, and the question is like, first of all, can we actually say something about the probability of this hard wall event? And then the second one, what actually happens under this conditioning with the field? And the answer was given, well, it's something which is called entropic repulsion. So, of course, once this elephant sees so many mice, but who wouldn't, he wants to run away. The question is like, how far away? And like, I mean, like, because when he runs away and maybe climbs the tree, so he loses energy, but then maybe he gets back his serenity. So the question is like, what wins? And serenity in this case is more like entropy. That's why it's called entropic repulsion. So actually the elephant prefers to run away, and in such a way that it actually can fluctuate. So this 2 square root of g log n, this g is 2 over pi. With my normalization, with your normalization, it would have been, I don't know, a different constant. But anyway, so this is actually the range of the infimum of the field, or supremum. So basically, the elephant, our GFF, prefers the freedom of fluctuation such that it doesn't hit the wall, rather than preserving energy. But also he won't run away too far, because afterwards it just doesn't make sense. Why would you, if you're already far away, there is no reason. So basically what they proved is that the norm, like at each point, the probability that phi x is more approximately equal to 2 square root of g, which is, forget this square root of g, log n, that would be the behavior of the field. So this is where the field will get transferred. So well, and then there is also like an actual estimate on the leading term in the behavior of the, well, in the estimating this hard wall condition, which is given by also some quantity which is equal to 4G capacity, where capacity is basically, I think it's, I think in physics it's the same as condenser capacity, or I'm not sure. Anyway, so now the question is, what if instead of the whole wall of like scary mice, we just keep one little mouse? What happens with our GFF? Will it, like, okay, so here I have a question for you. Let's do some voting. Well, it can still get super scared and run away all completely. Theoretically, because in one-dimensional case, it sort of can, I don't know, get distorted, and like the parts of it will fly away in two different directions. And then there is, okay, so this is not quite accurate, so actually there will be, of course, well, okay, some sort of a hole here, because we are not allowed to stay in this area. But, okay, any guesses? So who is for scenario number 1? Okay. So who is for scenario number 2?
What is n?
Where is n?
The number.
Here, okay, here let's do the n equal to 1. N equal to 1, so it's really, we get really distorted, so it's like we have to separate if we separate. Because we can't stay at 0. And who is for number 3?
Could you repeat the question?
Okay, so the question was, so we know like if you condition on the hard wall, then your elephant runs away. And my question is, okay, so now I don't want the whole, I don't want to condition on the field to stay away, or to stay positive. I just wanted to avoid a small interval. Doesn't matter how small it is. Any length greater than 0 is fine. And my question is to you, what scenario do you think will happen? And I want some voting, so I got some votes for 1, I got some votes for 2, I got some votes for 3, but in total there were 5 votes, so... No. Not temperature. Well, I mean, like my normalization of the... I mean, no one will be punished or anything. Okay, so who is for number 1 now? Okay, 1, 2, 3, 4. Okay, so what about number 2? Okay, and number 3? Okay, so actually people suggested that number 1 is the thing that happens. But no, actually the same thing happens as in the conditioning just on the hard wall. So actually, and that's why so we have the entropic repulsion. In this situation means that the field in the norm goes far away. However, it also doesn't exclude the first case. However, what we managed to show is actually that in some sense these spins, which are phi x divided by the norm of phi x, they sort of get aligned. And this is at any distance of size n. So basically, so this is rather a demonstration, again, of this 2 square root of g log n of the how far away the elephant will move. And this freezing of spins, that's however you prefer it to call, indicates that the whole elephant goes into one direction. Of course, this direction is, you know, especially if the interval is symmetric, it's like with probability 1/2 you go all to the right or all to the left. So this is our first result, and after discussing some further results that we have, I maybe sketch some, like an idea at least to how to get this result in our case. Okay, so now the n greater or equal than 2. And we are now conditioning on avoiding a ball. So instead of now a GFF like a 1 spin dimension, we consider this n copies and then condition again on the norm to be greater or equal than r within the dn. And then we still have the entropic repulsion, so the field, the norm, still pushes away. So the field really wants to run away. And we still have the lower band. What I mean by that, in this, well, here I have the lower band. Yes, and what we know the freezing of size. So here it was at all scales, at scale n as well. what we managed to show is that now we have also freezing of spins at microscopic scales, meaning that if x and y, if x and like this is an image of a point x, and this is a point of and y were close enough, then at mesoscopic scale and alpha, then somehow here they would be close enough to each other in the GFF. However, what we kind of didn't manage to get, but we believe that it's true, is that also this holds if, for instance, this is an image of a point 0 and this is somewhere n, like we sort of still don't know how to rigorously prove that they would be also close enough, so that actually my elephant won't stretch. So we know that it's R. We know that for close enough points, the images will stay close enough together, but what is still missing is that actually also at the scale n, this would be the case. Okay, but what was our original motivation? Our original motivation was to understand maybe spinor models at low temperatures by looking at these guys. And what this entropic repulsion tells us is basically that the typical point is already of order log n, meaning that the temperature at which we would be looking at spinor model is log squared n, which is like 2, and we've seen that there is freezing. So in the sense we send the temperature so quickly to 0 that it kind of wins this, order disorder phase transition, which non-existent for xy. But here it was it's for a fixed temperature. Here we kind of send the temperature just too quickly to 0. So what would be more reasonable to look at would be actually conditioning the massive field, because what's happening there is that actually the expected norm of the field for any n conditioned, again, on staying conditioned on staying outside of the ball radius r. Okay, so here I'm a bit cheating. I introduced you the Dirichlet method GFF, but here I'm using already the one on ZD, but I mean, I'll be forgiven, I hope. So anyway, we show that the expected norm of this field is uniformly bounded, meaning that there are definitely at least an infinite volume limit. We don't know, maybe it's not unique. And actually what happens in dimension 1, in spin dimension 1, is that independently of the mass, if R is, as long as it's positive, if R is large enough, there are actually there are at least 2 Gibbs measures which have the interaction potential of the basically messy field condition to stay away from the ball for all the lattice points. So in particular, there is no uniqueness, but what is actually our hope? So the conjecture, or like maybe the wish, so the massive GFF before conditioning, it has exponential decay. So our hope is for n greater or equal than 3, or at least maybe n large, to be able to say something like, okay, we are given some r. Then we want to claim that, if we are given r, we can choose mass small enough, depending on this r, such that the conditioning doesn't perturb my model so much, so that I still preserve the exponential decay, and then through this, basically, we would get some, exponential decay for spin-run models. So this was basically, this is the main motivation why we had all started looking at these things. And now maybe I can, how much time do we still have? 10 minutes? 10 minutes, oh perfect. Then I can actually go and explain some math behind it. Okay, so here I will discuss the m equal to 1 case, but some of the ingredients that I'll state here, they're also true for higher spin dimensions, and I will exactly mention which ones these are. So, how will we proceed? So we have our big box lambda n. What we will be constantly looking at are subgrids of this mesoscopic scale n alpha. So basically, we're looking at the subgrid. It doesn't have to be centered at 0. So we basically pick any x0 and center around it. Then the important quantities that will, for us, would be harmonic extension of this boundary, basically the values of the field on the boundary. And then, of course, I want to use the domain mark property of the GFF. So I define these phi betas to be exactly the differences which would give me independent GFFs in these boxes. And then, okay, here there are like some quantities which I'm introducing now because here there is a picture and I'll use them later. So what we will look at, so in some sense, what have we claimed? We have claimed entropic repulsion, and we have claimed that somehow we pick the direction. So what we will be looking at is the number of like first low boxes. By this we mean that we look at the boxes which have low harmonic extension, because actually what happens, well, basically this 2 log n, 2 square root of g log n, it comes from the push of the harmonic extension. And then the fields in the boxes, they're the ones that fluctuate. So what we want to find is somehow like the natural thing would be then to show that this number can't be large. Then the other thing is like, of course, we also have to get back to the original field, we need to, well, so here we're only looking at the centers. But the harmonic function around the center actually would be more or less constant. So now what we also need to understand is the fluctuations at the centers to get back to the original field. And here we're again looking at the bad points. So it's the ones where the field actually fluctuates quite a bit. So that is at least of order log n. And then, like, to get the signs back, what we will be looking at is, well, the number of positive boxes, and by positive boxes I mean here the boxes where the harmonic extension in the center is positive, and negative, well, minus harmonic is positive. Okay, taking this into account, we managed to prove these key ingredients, which basically would allow us to prove the rest. So these are like really the key steps. So, well, maybe let me start with the number of low boxes is negligible. So, meaning that, so what we want to show is that the number of these boxes where at the center is the harmonic function is of strictly smaller constant than 2 square root of g times log n size. So what we want to show is like, okay, that depending on this beta, and beta was so we were looking at so this is the parameter beta. So what we managed to show is that for any beta greater than 0, we can choose the mesoscopic scale, starting from which, so actually the alpha would be very close to 1 for us, such that, yeah, at these mesoscopic scales, actually this number can't be too large under the conditioning, of course, because otherwise it's actually not supposed to be there unless we condition. Okay, so this is the first step. So let me maybe mention, a similar thing was, a similar observation had to be done in the case where we just conditioned on being greater than r for the field or 0. But the way how we prove it is very different. So there, basically, how it followed, they were looking at how the infimum of the field behaves, and through there they got this 2 square root of g log n, that it cannot happen that there are too many boxes where, because basically, for them, the harmonic function was more or less positive. So they were looking at something like that. And then one could analyze it using like the supremum of the GFF. In our case, what we are rather using is that actually the range of the GFF, like the image of the GFF, is quite condensed, meaning that at all scales which are actually strictly below the 2 square root of g log n. So as long as we are at this scale, around this point the field, well, if one projects it, there are quite many like image points in the range. So that's it. So number of boxes with high fluctuations, this is a super easy, because basically here it's where you get, where one uses the domain markov property and one gets a sum of independent random variables with very small probability and variance, and then one uses Bernstein inequality and gets this easy band. Here nothing interesting happens. And then actually one of my favorite parts is where the centers peak is psi. So these two results also hold for n larger than 1. The first result, however, is only true for n equal to 1, and the problem is the following. So what are we looking at? So suppose we have more positive points than negative, we have more positive boxes than negative boxes. Then basically what does it mean, this event? It means that the interface between positive and negative boxes, like at the interface between the boxes where we switch from positive to negative, we have at least n to u half points, either where the jumps are very small, and by jumps I mean h beta minus h beta prime, where this was h at the center of the box, where this is like really small. And then the other possibility is actually when, say, for instance, like this, well, actually one can quantify, so the way it's quantified here is we are looking at so we are comparing these guys with delta log n, but to tell the truth, one can actually do it with k, where k is large enough, square root of log n. So actually we would know that there are not many, it can't happen that there are many jumps of order k square root of log n. But for simplicity, let's consider this one. So basically, there are two scenarios, right? So one I mentioned where there are a bunch of small points and one like small gradients, and the other case is where there are sufficiently many big jumps. And okay, for the small ones, the trick is very easy, since we know that the differences are, maybe actually we are not even looking at it. Yeah, so basically what we are doing is like we are looking at the boxes. Okay, so here I actually cheated a bit. What I'm actually looking at is at the, so we have this interface. Between positive and negative boxes. And what I'm looking at is rather something like, so I'm looking at n, so I assume that n minus is less or equal than n plus, which by symmetry you can afterwards, or yeah, treat the other case. So we are looking at the points where the field at the centers is smaller than minus delta log n, and the one where the field is between minus delta log n and 0 at the centers. So this would constitute, this sum, well, basically at the interface, if I only look at the negative parts, would give me order nu half points for both of them. And like to show that this guy is small, it's very easy. There you just, here you still work with our condition, event on linear condition, and basically, if I look now, if I now condition on the alpha grid and work under the, well, under the event where there are many of the points where I'm below the delta log n, here I just, at the end, because of the domain markov property, I can bound this whole thing. here, and by the product over these boxes with contributing to n between minus delta log n and 0. And then here I basically, instead of looking at the whole box, because here I would still have for all x inside this box some results, but I forget it, I just look at the center, and for the center, I think it's not in I. And for the center, basically, here I just use the basic bound, so this is between minus delta log n, and this guy has variance g alpha log n, so it's standard normal. But then because this number is at least n to u half, one can choose delta. Well, one would need to adjust delta depending on alpha, but for the next bound, we won't care how small delta is. So, but my favorite part is to treat this case, because what actually happens here is like, there is this really nice trick, which is also based partially on this idea from your paper, from Aurelio's paper and Christoph's paper, on where they basically show that the GFF, the gradients of the GFF on faces plus the gradients of GFF on what was it, edges? Yeah, along edges, that one is a white noise. So from there, I just steal the fact that it means that the eigenvalue of the covariance matrix, which corresponds to the gradients of the gradients of the GFF on edges, is finite. But then basically, what is this H hashtag, whatever? In some sense, this, if one restricts only to the centers, it kind of behaves like the Gaussian free field on the grid of order, well, this is approximately lambda n to 1 minus 1. And then, well, there are nice quantitative bounds that are available in the literature which actually allow to say that the field is nice. And how do we use it? So basically, if one knows that we have two fields, two Gaussian fields, zx and yx, and this is like has some covariance n0 cz. Okay, maybe let's better put it this way. And then we know that cz has a finite maximum eigenvalue. Then I can always find a field z tilde x independent of zx such that z tilde x plus zx is diagonalized with this lambda 2 times lambda max identity. And this is the trick that we are using, because basically what does it mean that the number where the boxes at the interfaces would be lower than delta log n? It means that there will be, these jumps would be at least of order delta log n, and there will be at least nu half of them. So these gradients, well, yeah, so these guys behave like the gradients of the GFF x beta plus, maybe let's pick direction and alpha E1. E1 or E2. Yes, and here my edges are either these or these. Okay, so what does it mean? It means that I can rewrite this event where this number is greater or equal than n to the power u half implies that the average over indicator functions of this event has at least nu half positive summons. And then this thing is dependent on the conditioning. However, we can basically make the trick of, so if this would be my dx, I can add the z tilde, well actually I can subtract it, and then I can divide it in delta half log n. And so at least it's either this one would be delta half log n, or this new z tilde would be greater or equal than, like each indicator function I split into two. And then basically the z tilde now are independent of the conditioning. So for them I can compute everything explicitly using again this Bernstein inequality. And this one is independent, it gives us again independent thing. So for this term I can use Bernstein, and for this one I can just use the union bound and the maximum, sorry. Yeah, for this one Bernstein. For this one union bound. So, I don't know, this trick, I just found this trick really nice because it kind of allowed us to compute. And I suppose my time is kind of over. So let me just tell you that using just these three ingredients, one can do everything that we stated there, the freezing and the entropic repulsion, and it's actually not too hard. If anyone wants to know some details, I'm happy to explain them. And I'm hoping that they will turn on the screen because I have some more elephants to show. But anyway, thank you. I'm kind of finished with the talk.